Hey students, in this video I'll explain about alcohols, phenols and ethers. So let's discuss the questions around the chapter alcohols, phenols and ethers, what was appeared in the last year's question papers in JEE Mains. Okay, so before that, what is the functional group for alcohol? It is ROH. Whereas for phenol, it is AROH. What is the difference between R and AR? R is a alkyl group, whereas AR is a aryl group. Alkyl, like saturated hydrocarbons. See, if you have a hydroxy group attached to a saturated carbon, then we call it as a alcohols. Whereas if the hydroxy group is attached to a carbon that is having a double bond, we call as enols. Enols are completely different from that of the alcohols, right? So usually you will be having enols like this. Whereas aryl is where you have a aromatic group like this. This is phenol. In case of ethers, it is RO, just like in case of alcohol, but one of the hydrogen is replaced by another alkyl group. This is your ether. So let's discuss what are the types of questions that will be asked in the exam from this chapter. Okay, so I'm taking up some of the questions which were asked in the previous exams. So we'll discuss the questions as well as the answer and the concept around it, so that it will be useful for you in the exams, right? Let's start. Okay, look at the first question. The compound here is phenol, right? By looking at the structure, you should be able to name it. Phenol. When reacted with, what is this? Chloroform. In the presence of base, it forms benzene. This is O minus Na plus, and this is aldehyde. So this is usually called a salicylaldehyde, and this is salicylate. Salicylate. Which salicylate? Sodium salicylate. Now can you tell me what is the name of the reaction? By looking at the reagents, especially these two reagents, can you tell me what kind of reaction it is? It's a named reaction. What is that reaction? It's a Riemann-Tiemann reaction. Riemann-Tiemann reaction. This is a Riemann-Tiemann reaction. So you have given with the reactant, reagents as well as the product. Then what is the question? The question is all about the electrophile involved in the above reaction. Obviously this is a electrophile. Why? Because you know that benzene is a nucleophile, because it consists of 6 pi electrons. So if at all any reaction that happens on the benzene ring, it should be the attack of the electrophile on the benzene, because benzene is already a nucleophile, because it is rich in pi electrons, that is 6 pi electrons. So that's the reason why the electrophile involved in this reaction. What is the electrophile involved in this reaction? Very simple, and it is very, very specific. That means you will come across this type of electrophile very rarely in throughout the chemistry. So you need to remember this a lot. What is that? Chloroform. See this one, how I'm writing the structure. CHCl3, chloroform. When treated with base like sodium hydroxide, what is the role of a base? Base is a substance that abstracts proton, means it takes the proton, it attacks this proton. What happens to this proton? Is eliminated as water. But you can see the electrons attached to the carbon. See, this is the hydrogen that is eliminated with the help of this hydroxide. These electrons will delocalize, right? So in order to compensate the electrons of this, one of the chlorine gets eliminated. How the structure looks? Carbon, you have a chlorine, we have a chlorine. These two electrons over here. Got it? These two electrons are present here. This is called as carbene. What carbene? Two chlorines. Dichlorocarbene. This is the first step, and this is the electrophile. See, electrophile means should be the presence of positive charge. For example, see, CH3 plus. This is a electrophile. Why this is a electrophile? Because carbon is tetravalent, but here carbon is bonded to only 3 hydrogens. The 4th valence is missing, and that is the reason why it is gaining a positive charge. So carbon wants to become stable by accepting electrons, so immediately it will attack a nucleophile. In this case, the carbon case, it is even more reactive. Why? Because it is deficient by 4 electrons. You can see here the valence of the carbon is only 2, so it is even more reactive than this. So this is carbene, the reactive intermediate, and the electrophile in the Riemann-Tiemann reaction. You'll come across the carbons very rarely in chemistry. So this is one specific example where you'll come across, and you need to remember this. This was the question asked in Mains 2006 about the Riemann-Tiemann reaction. So one more thing I want to convey over here is, not only the reactions, you need to go through the mechanisms also. It's not like, you need to remember what is the reactant, what is the reagent, or what is the product. Not only that, along with this, you need to understand the mechanisms as well. So this is one such example. Hope you understood. Look at this question. The increasing order of the rate of HCN addition to compounds A to D is. Okay, so we are adding hydrogen cyanide to compounds A to D, right? So what is HCN? H plus Cn minus. Now the increasing order of the rate of HCN addition, that means when you are adding hydrogen cyanide, which of these will undergo the reaction faster? What is this reaction basically? This reaction is nucleophilic addition reaction. Is basically nucleophilic addition reaction. Means whenever you are adding a nucleophile, right, to the electrophile, so there is possibility of addition reaction taking place. Now you have 4 options over here. Among these two, which reacts faster to this reagent? So you need to arrange in the increasing order of their reactivity. Have a look at this. Option A, B, C, D. This is formaldehyde, acetone, then you have 1 methyl and 1 phenyl. Here both the phenyl. This is benzophenone. This is acetophenone. Right? Acetophenone is benzophenone. This is simply acetone and formaldehyde. Formaldehyde will react faster in this way. And forms cyanohydrins because of the presence of very less sterically hindered groups. You have just hydrogens over here, right? Just the hydrogens, but in this case you have both the methyl groups, okay, which is sterically not favorable. But in this case you have one bulky group, that is phenyl. In this case both are phenyls, like this, right? So it is A undergoes faster, you can see. That means A. You have 3 options, so you can eliminate option number 1 here. Among these 3, after A, what is that? This is acetone, because you have both the methyl groups. In this case you have one phenyl which is more bulkier than that of the methyl. So before A, now B. So I can eliminate option 2 as well, because A and B. Among C and D, look at this. You have both the phenyls in this case, but you have one phenyl and one methyl. That means the nucleophile can attack from here, though it is bulky here. So option D, option C and option D is like this. That means formaldehyde is more reactive towards the nucleophilic addition reactions than that of the acetone, than acetophenone, than benzophenone, based on steric hindrance, right? So carbonyl compounds undergoes nucleophilic addition reactions. These are the characteristic reactions that takes place. Apart from the addition elimination reactions, oxidation reactions and reduction reactions, carbonyl compounds undergo nucleophilic addition reactions. Okay, moving on to the next question. A solution of 1-chloro 1-phenyl ethane in toluene racemizes slowly in the presence of a small amount of, this is antimony tetrachloride, due to formation of. Okay, so before we solve this, let's write down the structures of the compounds given here. 1-chloro 1-phenyl ethane. Okay, so this is eth, right down 2 carbons. 1-chloro 1-phenyl, this is 1-chloro, and again to the same carbon there is presence of phenyl. Now balance the rest of the valency of carbon by placing hydrogens. Now this is your 1-chloro 1-phenyl ethane, and they have given you, this is LiVo. Okay, because negative sign, right? So this is LiVo. Now in toluene racemizes slowly. You understood, right, this one, because this is a chiral carbon where you have the carbon which is surrounded by 4 different groups, and this is another groups. So that's the reason why you can mention here as a LiVo. Okay, this one racemizes slowly in the presence of small amount of antimony tetrachloride. So this is due to formation of what? Means whether it is formation of carbenes, carbocations, free radicals or carbanion ions. Okay, you should understand the nature of the reagent what is added here. Antimony tetrachloride. This is a Lewis acid. What is Lewis acid? Lewis acid is an electron pair acceptor. Lewis acid is electron pair acceptor, means it accepts the pair of electrons from a compound. Means when I have added antimony tetrachloride to this compound, it accepts the pair of electrons of chlorine, because this is the only good leaving group present in this compound. 1-chloro 1-phenyl ethane, it cannot pull hydrogens because the electronegativity is almost similar between the carbon and hydrogen, right? And even the phenyl. So the only good leaving group that is can be eliminated from this compound is chlorine. So this Lewis acid accepts the pair of electrons of chlorine in this way, and it forms SbCl6 minus. So once this is eliminated, electron pair acceptor, that means it is taking up the pair of electrons attached to the chlorine. What is left now? Look at this compound, carbon, this is hydrogen, then you have a phenyl. This methyl group is intact as such. So due to loss of this pair of electrons, carbon gains positive charge. Hence presence of, due to formation of carbocation. So this is the carbocation that is formed as an intermediate in this reaction. Hope it's clear to you. Moving on to the next question. Which of the following on heating with aqueous potassium hydroxide produces acetaldehyde? Okay. Now you need to take out each and every reactant and treat it with aqueous potassium hydroxide so that acetaldehyde should form. That is actually okay. Let's try out. For example, if CH3COCl, if this is treated with aqueous potassium hydroxide, in this I'm just taking only OH minus. So OH minus here, it acts as a nucleophile, attacks here and then forms CH3CO minus Cl, then OH. No, so here there is nowhere there is formation of acetaldehyde, because the compound formed after this is this. What is this? Acetic acid, right? This is acetic acid. So option 1 can be eliminated because the compound formed upon treatment of acetyl chloride with aqueous hydroxide, potassium hydroxide, formed is acetic acid. Let's try with the second one. CH3, CH2, Cl. So we have positive charge here, negative charge here. When this is treated with again OH minus, very simple, attack of negative charge, replacement of this one. The compound form here is CH3, CH2, OH. Means I can eliminate this as well, because this is leading to the formation of ethanol. Whereas this one, acetic acid. But what we want? Acetaldehyde. So the option should lie between 3 and 4. Okay, try with this next one. CH2, Cl, CH2, Cl. This when treated with OH minus. So one of the carbon gets attached and this is eliminated. You get the compound like this. Is this acetaldehyde? No. So the answer should be in this one. So how do you write on the mechanism of this? CH3. This is CH. This when treated with OH minus, it should be like this. Look at this. Again, with excess of OH, you get like this. These are Zem diols. These are Zem diols. What is a diol? You have a carbon that is attached to two hydroxy groups. That means two hydroxy groups are attached to the same carbon. So this is a diol. What kind of diol? Zem diol. But in this example, if you see, even though there is halogen that can be replaced with OH, then this is called as vicinal diol. Vicinal diol. Vicinal diols where you have a two hydroxy group present on the adjacent carbons. Zem diols, two hydroxy groups present on the same carbon. Zem diols are always unstable because of the hindrance again. So what happens here? Look at the mechanism. CH3, this CH, this is eliminated as a water and then forms double bond O. This is nothing but acetaldehyde. Dehydration is happening. I'll show you. If you want the mechanism, you can see here where OH is like this and here also OH. So one of the lone pair of electrons attacks this. So immediately these electrons pull here and this will be eliminated. So in this way there is formation of acetaldehyde. Means the option over here is this one. CH3, CH, Cl and Cl. Means 1,1 dichloroethane when treated with aqueous potassium hydroxide undergoes dehydration as well, because there is formation of Zem diol which was unstable and there is elimination of water that leads to formation of acetaldehyde. Let's move to the next question. Okay, look at this. Chlorination of tertiary butyl benzene gives substantial amount of ortho substituted product, while its bromination gives nearly negligible amount of the product. Which of the statement is correct? So before looking into the statements, let's understand the question. Chlorination of tertiary butyl benzene. So write on the structure of tertiary butyl benzene. Benzene, tertiary butyl. Look at this. What is this? The same can be replaced like this, right? To make it understand even better, write on the structure in this way. This is tertiary butyl benzene. Gives substantial amount of ortho-substituted product. Which one? Chlorination. Means when you do chlorination, you are getting a little less amount of the product. Because why it is very less? Because of the bulkiness. You can see here. This is a bulky group. Usually when you do chlorination of tertiary butyl benzene, the major amount of the product will be para-substituted product because of the ortho effect, which we have discussed in the previous classes. But you get a minor product that is ortho-substituted, whereas its bromination gives nearly negligible amount. Means the product, the same thing. Here you get bromine, but here if you say there is only 10%, I can say here only 1%. What is the reason? That's what they were asking you. Hope you understood. Okay, whenever you undergo halogenation of tertiary butyl benzene, majorly the para product should predominate because of the steric hindrance present at the ortho groups or ortho substituent, which we call as a ortho effect. But still there is presence of ortho product, very minute amounts, that is around 10% assume in the case of chlorination. But if you do bromination, the amount of the product is still lesser. What is the reason? That's what they were asking you. Look at the first statement. The benzene onium ion formed in the first case is more stable than the second case. It is difficult to produce Br plus ion than Cl plus ion. No, because you have the same Lewis acid. That's why we are using the halogenation reactions. Okay, the role of Lewis acid in either chlorination or bromination remains same. So it will be easy for us to form either chlorine cation or bromine anion. Difference in size of the electrophile. Yes, chlorine is lesser. I mean, the size of the chlorine is far lesser in size than that of the bromonium ion. And chlorine is more reactive than bromine. It's not like that, because they should be an electrophile to attack on the benzene. Okay, they should be an electrophile. Whether what kind of electrophile doesn't matter. So here it is the size that affects. Already there is a presence of tertiary butyl group and it is blocking the ortho positions. But if you use bromine, even more bulkier. So this position is highly negligible. That means there is least amount of the product that you can expect at this position. Got it? So that's the reason, difference in the size of the electrophile. Which of the following statement is true? Orthoxylene is sulfonated most easily. Okay, understand. Let's understand the options here while writing the structure of xylene. What is xylene? You have methyl. Orthoxylene means you have one more methyl, right? Xylene is sulfonated most easily. Paraxylene is sulfonated more easily. I'm writing the structure here again. Okay, this is paraxylene. Metaxylene, all the three xylenes are sulfonated at the same rate. So sulfonation, this is one of the electrophilic substitution reaction. Now when you are adding concentrated sulfuric acid, so what happens here? This is ortho, this is ortho. Basically ortho positions are favored. Now for this is para and this is para for this. Whereas here these two are orthos. And here this one is blocked because of the presence of groups here. So among these, which one do you think more easier? I'll go with para. What is the reason? What is the reason why? Because you can see here, these are present, the para substituents are present far away from the substituents over here, whereas in here, this case and this case, this is blocked. Are you understanding? So orthoxylene is sulfonated most easily. This will be orthoxylene. And paraxylene is sulfonated most easily. Metaxylene is sulfonated most easily. No. Usually we can sulfonate, all the 3 xylenes are at the same rate, right, irrespective of the positions where they are. Sulfonation can take place. If at all there is presence of any bulkier groups like tertiary butyl groups, then in that case it may differ. The structure of the major product formed in the following reaction. So they are asking only the major product here. The structure of the major product. So you have a benzene and this is CH2Cl, benzyl chloride, and you have methyl. So I'm making CH3 here. This is CH2Cl. When treated with sodium cyanide, what happens? Sodium cyanide dissociates as like this. You have partial positive here, partial negative here. So once this attacks this carbon, what do you get? CH2Cl. Now you have a methyl. This does not affect methyl group, right? Methyl group is very resistant. It cannot be eliminated easily. It's not like halogen. Halogens are good living groups, right? But methyl group cannot be eliminated from this. Whereas you have a partial positive and partial negative charge, and chlorine can be eliminated, so that this nucleophile attacks this carbon and forms benzyl cyanide. And moreover, cyanide cannot attack on anywhere on the benzene ring. You have only 5 electrophilic substitution reactions, that is nitration, sulfonation, halogenation, alkylation and acylation. Apart from this, any other electrophile cannot be attacked. Here Cn minus is a nucleophile. One nucleophile cannot attack another nucleophile. So this sort of reaction cannot never happen. And look at the fourth one or third one. Even third one can be eliminated because they are attacking the nucleophile onto one other nucleophile. Among 1 and 4, here there is presence of CH2CN and they are replacing this CN also. But CH3 cannot be replaced. So even this cannot be possible. The only possible option over here is option 4. Have you understood? So this is what kind of reaction? This is SN2 reaction, where nucleophile is attacking the carbon from the back side and the halogen is leaving from the front side. So the whole configuration is getting inverted, which we call as a Walden inversion. This reaction of trans 2-phenyl 1-bromo cycloheptane on treated with alcoholic potassium hydroxide. So before looking at the options, let us draw the structure of this compound. Cyclopentane, how does it look? Cyclopentane, right? 2-phenyl 1-bromo. Okay, I'm just writing here as 1-bromo. Then you have 2-phenyl. Okay, this is phenyl group. Now, trans 2-phenyl 1-bromo. So how do you represent trans in this structure? It's very simple. Make it, this bond will be bolded edge bond and this will be like this. The bonds are reversed. So here you have a bolded wedge bond and this is a dotted wedge. Now I can say they both are in the different configuration and I can say this as a trans. Now let's draw the hydrogens present adjacent to it, because each carbon is having one bromine in this structure in this way as bromine and other is the hydrogen. Here also you have one hydrogen and the other will be phenyl. This is trans 2-phenyl, here 1, this is 2. Trans 2-phenyl 1-bromo cyclopentane. When treated with alcoholic KOH, alcoholic KOH means elimination mechanism. If it is aqueous KOH, then it is substitution. As this is alcoholic KOH, then elimination should take place. How does the elimination take place? Alpha elimination. That means hydrogens, you have a halogen here, right? Hydrogen from the alpha carbon is eliminated. Alpha carbon for this bromine is, this is a alpha carbon and this is also alpha carbon. Means hydrogen from here, either any of this hydrogen or this hydrogen can be eliminated. Now which hydrogen can be eliminated? Either to your left side or to the right side. I cannot eliminate this hydrogen because this bromine and hydrogen are present on the same configuration. They have same configuration, cis. For E2 mechanism to takes place, it is also called as anti-elimination. Means stereochemically they should be opposite, right? Then only you can eliminate. But here you have a hydrogen and bromine having the same configuration, that is cis configuration. So this hydrogen cannot be eliminated. You can eliminate the hydrogen which is present on your left side. If I eliminate that hydrogen, it will be hydrogen, your hydrogen intact as such, then you have a bond, double bond. So this is called as 1, 2, 3, 4, 5. Means 5 phenyl, right? If you see here, okay, sorry, this should be your 1, 2, 5. 2 phenyl cyclopentene. Is that clear? Any doubts so far? What has been taught to you? Yes, the answer is this. Okay, so I'm signing off. If you have any doubts, please put on chat. We'll clarify your doubts. Thank you.